So welcome back after the coffee break. We are now ready for the next talk. It will be Axel Osmond, who will tell us from the Université de Paris, who will tell us about stable pseudofunctors, local right bi-adjoints, and two geometries for topoi. Please, Axel.
So I'm very happy to present you this work. So if I can. It worked 5 minutes ago. Okay. Oh, okay. Very good. Yeah. Thank you. So, so in this work, my purpose is to introduce a two-dimensional framework in order to formalize some observations that arose when I was studying the spectral construction. So before going into this categorification process, I should present you a bit what is the spectral construction. So this is something you may have already met for some of its instances as the spectrum of a commutative ring or stone dual of a distributive lattice. And roughly speaking, this is a construction through which you correct a situation of local adjunction with a defect of uniqueness in the universal property of a unit into a proper situation of adjunction by exploiting some hidden geometric behavior. And in this work, I am going to categorify the situation from which you construct spectral construction. And I won't talk of the spectral construction itself, but more of the situation from which you construct ones, which I will label as geometries, which is an umbrella term encompassing different possible axiomatization of this idea, because there are a lot of different possible axiomatization using different formalism as someone with a Grothendieck topoi or with a model theory or purely categorical. But whatever the way you state this this notion, it boils down at some point to something being a local right adjoint. So what is a local right adjoint? This is a functor that lacks a global left adjoint, but which is such that if you look at the restriction at each slice, it has locally a left adjoint. And this concretizes the presence of, in the rich object, of a cone of local units, jointly assuming the property of a unit. And in fact, this notion can be rephrased in an alternative way, which is a notion of stable functor, which is a notion which is more akin to factorization and orthogonality, in which you state that any map toward an object in the range of your functor factorized as a map in the range of the functor on the right, and on the left, a map enjoying some kind of strong orthogonality property relatively to map that are in the range of your functor. And the ingredient of geometry would be should be at least a category, locally presentable category of would say ambient object, a category of local object and local map, and between them a local right adjoint, which will in fact often satisfy some accessibility properties, but in which I won't give detail. And then when you have such a situation, you define a class of étal map, which are map that have also an orthogonality property relatively to map in the range of your functor, that is relatively to local map, and amongst which you have the local unit of your local right adjoint. And you may also require additional property, but what I am interested to is the kind of geometric-like behavior that are hidden in the opposite category of ambient object. Because local object will behave, in some sense, as focal spaces that are spaced with an initial point, and étal map will behave a bit like inclusion of saturated compacts. And in fact, the spectrum is a functor that concretizes this intuition by constructing a topos for each object made of the étal map between below it, and whose points are to be the local unit of this object. And this defines a functor into the B category of the opposite B category of Grothendieck topoi. And so you may have met a lot of some example of this construction which has a lot of instances as a spectrum of a commutative ring, the Zariski spectrum for commutative ring, which is induced by the stable inclusion of local commutative ring and conservative ring morphisms, or other notion of spectrum for ring as a Pierce spectrum or the étal spectrum, also stone duals of distributive lattices, induced by the inclusion of local distributive lattices and some kind of one conservative morphism between them, or more exotic notion as a more recent spectrum for integral rig or for MV algebra and so on. But in each case, what is interesting is that the spectrum sends local object to what we call local topoi, and it sends local map to a class of geometric morphism we could call terminally connected, and étal map to a class of geometric morphism called pro-étal. And this means that for any spectrum, any notion of spectrum, you have a kind of factorization of the spectrum through the inclusion of the B category of local topoi and terminally connected geometric morphism. And this led to the question to know whether in some two categorical sense, this inclusion itself of local topoi and terminally connected is dual to be stable to some kind of two-dimensionally stable pseudofunctor. And if eventually, so this led to the question to know if we can define a two-dimensional geometry, for instance, for the logoi that are the opposite of Grothendieck topoi, and if there are other instances of such a construction. So this is what I will try to answer to during this talk. So to do that, I will categorize the notion of local adjoint and stable functor. So I will say that a pseudofunctor is a right bi-adjoint if its restriction at each pseudo-slice has a left bi-adjoint. And this means that any map towards the range of your functor will factorize in a unique universal way through a canonical invertible two-cell as a local unit, followed by a map in the range of your functor. And you will also have automatically some kind of a coherence condition, which state that if you have a map in a local map in your domain, the domain category of your functor, then the Beck-Chevalier mate of the natural equivalence expressing pseudofunctoriality of U will be always a pointwise equivalence, which in fact just means that if you post-compose a map with a map in the range of your functor, then you do not change the local unit through which it factorizes. And in some sense, this is related to the fact that local units are initial objects in the connected component of the comma under their domain they live in. But now I am still interested into categorizing also the alternative way to state local adjunction, which is stability for a functor, because in the example I will construct, I will use orthogonality and factorization ideas. And so I would like also to categorize stability, and to do so, I will have to categorize the property of the morphism involved in stability, which, so I would say that for a pseudofunctor, a morphism is generic if for any pseudo square, as below, you have a decomposition as a pasting where the right part of the pasting must come uniquely from an invertible two-cell in your category of local object and local map. And moreover, you have to require some some pseudo-functoriality of this choice of a lift relatively to morphism of pseudo-square. And now you can define a bistable pseudo-functor as a functor such that any map into an object in the range of your functor admits a canonical factorization through a canonical invertible two cell as a generic morphism followed by a map in the range of your functor. And this must be unique in some suitable two-dimensional sense. And now you can prove that those two notions are really the same. So if you have a bistable pseudo-functor, then you can canonically construct at each object the left adjoint at the slice over this object just by returning for a map over the image of this object the local map in the right part of its factorization. And for two cell, you use the diagonalization of pseudo squares. And in the other direction, if you have a local right bi-adjoint, then the generic morphism are in fact the ones that are equivalent to the local unit that factorized. Now I am happy with this notion because to construct example, I am going to use bifactorization systems. So there is a straightforward way to categorify by factorization system and orthogonality. So for instance, say that a map is left orthogonal to another map if for any pseudo square from this map to the second one, that is a square which commute up to an invertible two cell, you have a decomposition of the invertible two cell as an invertible left two cell and an invertible right two cell, which are unique in some suitable two-dimensional sense again. And you will say that you will define a bi-orthogonality structure as a pair of class of maps such that the left class is exactly the class of maps that are left orthogonal to the right one and conversely. And then you can define a bifactorization system as the data of a bi-orthogonality structure, and for each map, a choice of a canonical two cell, decomposing it as a left map followed by a right map, enjoying again some kind of universality in the good two-dimensional sense. And bifactorization systems enjoy properties that just categorify the properties of factorization system in the one categorical setting. For instance, both classes are closed under composition, and so they contain equivalences, and equivalences are the ones that are both in the same classes. And also what is important is that you have some you have also the analog of cancellation property of left and right classes, which are, for instance, for the left class, the fact that if you have a left map which decomposes through an invertible two cell as a left map followed by another map, then the other map must actually be also a left one. And then, if you have a bicategory with a biterminal object and a bifactorization system on it, then you can classify the object accordingly to the class in which lies their terminal map into the biterminal object. For instance, you can define left object, which are objects whose terminal map is a left map, and consider the sub-bicategory of left object and left map between them, and any two cell between those left map. And you can also, on the other hand, consider the subcategory of right object, which in fact is automatically full, two-dimensionally full subcategory by cancellation property of the right maps. And in fact, it is even a bireflective sub-category, which is a categorification of a well-known result in the one-dimensional case. But what I am interested in is the property of the left object. Because if you look at the opposite of the inclusion of the sub-bicategory of left object into your ambient bicategory, then you get a bistable pseudofunctor, which happens to be faithful. And the generic morphism for this bistable pseudofunctor are exactly the opposite of right map from a left object into an arbitrary object. This can be proved just as an easy application of a right cancellation property of left maps. And also it's relativized over any object. But also what you can do is to refine this construction by specifying a subclass of left maps, which we call a specified left map. Sorry. You can do this if your class of specified left maps have a kind of right cancellation property along left maps, which is that if you have an invertible two cell as below, with a decomposition of specified left map has a left map, an ordinary left map followed by a third map, then the third one must be a specified left map. Then the bistable inclusion get of a left object refines to a bistable inclusion, inclusion of the opposite of the big category of specified left object and general left map between them. And now I am going to apply this template in order to construct two geometries for Grothendieck topoi using factorization system for geometric morphisms. So there are a lot of very cool factorization systems. For instance, the hyperconnected localic factorization, the surjection embedding factorization, and you can directly apply the first version of the construction to those ones. And but what I am going to describe more precisely are the factorization related to the connected étale factorization of a geometry of a locally connected geometric morphism and their subsequent generalization. And the key idea of this construction will be that you can classify geometric properties of Grothendieck topoi accordingly to the property of their terminal geometric morphism into set. So, there is a well-known factorization system for locally connected geometric morphism, which is the connected étale factorization. So where a geometric morphism is connected if its inverse image part is full and faithful, while on the other hand, an étale geometric morphism is the one you get as the projection of a slice of a topos. And those two classes are known to be bi-orthogonal and to form a factorization system for locally connected geometric morphism, which give you a bistable inclusion of the opposite category of locally connected Grothendieck topoi and connected geometric morphisms between them into the bicategory of locally connected Grothendieck topoi. Recently there was a generalization of this factorization system for essential geometric morphisms, but you get this by relaxing the connectedness condition on the left. So, and to do this, introduce a class of terminally connected geometric morphisms, which are geometric morphisms whose inverse image part lifts uniquely global element, which means that if you have a global element of the inverse image of an object, then it must come uniquely from a global element of this object. And you can show that terminally connected geometric morphisms are left orthogonal to étale 1. And it was shown that essential geometric morphism factorize uniquely this way, which give you a bistable inclusion of connected and locally connected Grothendieck topoi with terminally connected geometric morphism between them into the bi-category of locally connected Grothendieck topoi and essential geometric morphism between them, where there the local connectedness is automatic for object, because topos is locally connected if only if its terminal map is essential. But I am not very satisfied with those inclusions, because in those situations, left objects are defined by some connectedness property, which is a bit too coarse regarding to what you would expect for local objects. But recall that you can specify the object you want as a left object. I will say the good notion I would like to use is the notion of local topos. So a geometric morphism is local if its direct image part has a further joint, and a Grothendieck topos is local if its terminal map is a local geometric morphism. And it is known that local geometric morphism have a right cancellation along connected geometric morphism. And in fact, this slightly generalized to the following property, which is that over set, if you have a terminally connected geometric morphism from a local topos, then the codomain topos also must be local. And because of this, you can then refine the previous B-stable inclusion by looking at local topoi, but we can do even better. In fact, we can generalize the terminally connected étale factorization to arbitrary geometric morphism by relaxing the right part and looking at pro-étale geometric morphism, which has co-filtered limit of étale geometric morphism over the codomain. And those pro-étale geometric morphisms still are right orthogonal to terminally connected one. And in fact, you can factorize any geometric morphism as a terminally connected geometric morphism followed by a pro-étale one. And to do so, you have to choose, you have to remember first that a factorization of a geometric morphism through an étale geometric morphism is the same as the name of a global element of the inverse image part. And then you can use, if you choose a site of definition for your codomain topos, you can look at the category of global element of the inverse image, which is co-filtered because your geometric morphism comes from a flat functor. And then you can look at the co-filtered B limit of the étale geometric morphism under those global elements, and you can prove that the left part is actually terminally connected by using a formula by Dubuc and Yurtman about co-filtered B limit of Grothendieck topoi. So, and this gives you the expected stable inclusion I promised to you, which is the inclusion of local topoi and terminally connected geometric morphisms into Grothendieck topoi. And I won't describe what is the spectral construction relative to this way of constructing geometries, but I can tell you a bit of what we will get for this example. First, the decomposition as a co-filter limit will mirror some condition you generally put on local units, but also you will know that in some the spectral site should be the category of étale geometric morphism over your topos, and you know this category to be truncated. These two categories to be actually one category equivalent to your topos, and the spectral topology should be some kind of étale topology on this site. But this is just an externalization of the canonical topology, and by a well-known result exhibiting any topos as a shift topos over itself with the canonical topology, you will know that in some sense, any Grothendieck topos is the spectrum of the logos it corresponds to. That is of itself, but seen is the opposite category. And that's all, and thank you very much.
Merci beaucoup, Axel. So we can have a couple of questions. Paul Taylor has a question online. Please, Paul.
Firstly, thank you for the credit to me at the beginning of your talk. So I remarked to other people that this subject has gone through different periods of being fashionable, and the time when Francois Lamarche and I were involved in this seemed to have been forgotten in the theory. So I'm pleased to see that you're to get some credit. Now you have a very ambitious research program. You're doing things for toposes that I'd only conjectured and never written up for spaces. Now, there's at least two ways in which factorization systems come into this subject, and I wasn't completely clear which of them you were generalizing. So one of them was the way that I chose to define, that I found the best way of defining stable functors. And I recently discovered that my definition doesn't quite give a factorization system. It's a bit weaker. So that's something you might look into and see what you have to say about it. Do I have anything more useful to say? No, I don't think I have anything else useful to say on this subject. But anyway, I'll post my website on
there. So because I only very partially heard what you said at the end.
I'll send you an email.
Okay. Oh, very well. I will be very happy because your paper on a stable functor was very important for me to understand this notion. So I would be very happy to discuss this topic with you.
Thank you very much. Do you happen to know whether Yves DS is still with us?
Sorry?
Is Yves DS still with us? He must be about 80, I think.
Okay. Okay. Yeah. No, but I will. If you want, I will send you an email and we can.
Okay. Is Yves DS still alive?
Which? Sorry,
Yves DS.
Ah, yeah. Ah, sorry. No, in fact, I don't know. I tried to contact FDA some time ago, but I had no answer. And of course, I would like to discuss that thing with him, but I don't know if it's possible.
Somebody else might know. Dominic might know, for example.
So we have a question from here. So Walter.
Just since we are talking about history, before Yves DS, there was James Caput, who was a student of Kennison. So the concept of local adjunction, I think, appears first in a 1972 paper by
But
Caput.
there was also your paper in German about
yeah. Thank you.
So let's thank Axel again.